Hello, this is Jeff, and let's call this a test stream. Trying to get things working with YouTube live streaming, and there's some differences, and I had some initial problems getting it to work, so I think I might have a successful stream here today. Yeah, I thought I would just, I don't know, talk to myself for a couple hours and write some code, which I was going to do anyway. And so I'm actually working on my Basecode bootstrap compiler. And one of the things that I'm implementing is the ability to have a fast function or fast foreign function interface. And I had started with a particular implementation for the FFI instruction in the interpreter. And I kind of, I don't know, I as usual, was kind of doing some dumb stuff here. Actually, you know what? Hold on a sec here. Chat and everything works differently with YouTube. There we go. Let's see if I can shrink the window. Because I'm used to having my IRC chat on the left, so I can see it. I can't really see the YouTube chat. Now I can. All right, good. Okay. And let me double check. Sorry, it's going to be like lots of little playing around with stuff. So Nightbot still hasn't joined that I see. Well, maybe it has. I don't know. No. Yeah, Nightbot, it's picking up statistics from the channel, but it's not in the chat yet. It hasn't joined the chat. Oh, there it goes. Just slow. Okay. All right, good. Anyway, what was I saying? So, yeah, I had started implementing this, and so these are like an example. Like if I had a function called printf that had an external prototype of something like this, and then I had an example where, you know, I'm printing a float and I'm calling the square function and passing this value, you know, that would get translated into the following byte code essentially. We'd have the string somewhere in memory. We'd push the double as a binary value. We'd move a register with the address of the function, which we get this by dynamically loading the shared library that has that. And then we would call the fast function interface. And then this is the address of the function we're calling. This is the return type we want. And this is the number of parameters on the stack. And then, you know, of course, keep in mind the compiler is generating this code. So the compiler has some context around what's going on. And then, you know, in this case, this returns a double. So we duplicate it, we pop one off, and then we push the address of the printf string, and then we move the address of the printf function into the I0 register, and we call the printf function. So this is like roughly what it would translate into, but the underlying library that I'm using to make the dynamic calls into the shared library, which is called dynCall, it needs type information both on the return side. It needs to know what calling mode to use. It needs to know what the return type is. It needs to know what the type of all the parameters are on its internal execution stack, because dynCall is essentially like a it's like a little mini virtual machine on, you know, on its own. And so I had done this really cheesy bit mask thing to kind of like, this second value here actually has different configuration flags in it that tells it what the calling mode is and what the return type is. But then I hit a snag because I didn't realize I would have to distinguish the types going into the call. So, hey, King Flipping Hips, I just started. It didn't miss much. Yeah, I've been trying to get YouTube live streaming to work, and I've had some challenges, and so this is kind of, I think I finally got everything configured properly. And oh, hey, Vesley, okay. So yeah, so I thought I'd do a couple hours or whatever just to kind of test it out and see how it works. And after I do this, right, I'll have some information about maybe how I could do simultaneous streams, you know, and that's really what I'm trying to figure out, is like how I could simultaneously cast to both Twitch and YouTube at the same time. And so I'm trying to figure all that out. And I have a cold. Okay, so anyway, the net on this is that I realized I was stupid yesterday, because the way that the shared library stuff works, I have this symbol address map, right, that right now it just has the name of the symbol and the pointer to it, but we're going to change that, and we're going to add another map that's global, or, you know, static on the shared library class, I guess, so that we have an address to this new type. So I think we're going to add a struct called function signature T, and this guy is going to have the symbol, he's going to have the void pointer he's going to have number arguments. He's going to have a FFI return types. He's going to have an FFI calling mode. And these can actually just be, they don't have to be bit masks anymore. And then we're going to have a vector of FFI, actually, return types T. And let's rename this to FFI types T. I think what we need to know also try. I'm just looking at the dying call documentation here. Okay, yeah, I think it doesn't. Okay. I think that'll get us what we need. And the calling mode can be C default, I think, for like 99% of the cases. And we can default the return type to void type. Number of arguments would be 0. This would be null pointer. Okay, so then our symbol address map is going to be function signature T. Okay, so so the compiler is going to be calling this thing. Yeah, this stream will be saved. It'll be archived. I'll be releasing it kind of similarly to the way I do with my other archive streams. So DynLoad, which is part of the DynCall library, it has an abstraction around loading shared libraries, right? So I have this shared library T, which there's a collection on the terp of shared libraries by path, name, and the shared library. And there are helper functions on here that let you load a shared library. And this is how the compiler, like there's mechanisms in the compiler, in the language, where we can specify things that are foreign, and we can load a library for that. And all that works, but what you get, right, is an ELF file or a DLL or whatever. It's basically just a hash table of a name, a string, to an address. That's it. So if it's a function or whatever, there's no metadata about those functions. But the compiler does have metadata about the function, right? So because in the language we have to specify a prototype, a foreign prototype, so it knows what that thing is, how to call it. So when we go through in the compiler and we handle the foreign directive and we look at the prototype, that's when we would call load library. So I should be checking here to make sure that the library, we don't load the library twice. But I'm realizing hey Blackburn, how's it going? Doing okay. Going through my list of things that I needed to do, and one of them was to get YouTube live streaming to work. So I'm actually thinking let's roll this back. So as far as the shared library is concerned, it has a I gotta change my map here. It has a list of symbols to addresses. That's what it has. And that makes sense. That's all it knows. Okay, so the interpreter has a map of addresses to function signatures. So what's the compiler going to do? The compiler is going to say, oh, I have this actually, when you do that, just pass in. Oh no, but it doesn't. No, that'll work. Pass in the function signature T. So the compiler is going to say, I have this foreign function that I know about, and it's going to tell the interpreter about that. And then I just realized that the signature probably needs a reference to the shared library that it came from, right? Because you could have two shared libraries that export the same symbol, and because of the way those are going to get mapped to unique addresses. But I need to know which one the compiler's talking about, right? And so the compiler's going to have to tell me. So I think generically, this is not a runtime thing. This is just a compiler thing. I could put the path on here to the module that it comes from, right? So if you import something from, you know, OpenGL or from the format library or something, right? So if I open up my vector2, right? These don't have any decoration on them. So the assumption is that they're coming from the compiler. So that means that the compiler binary, the interpreter automatically loads and catalogs the symbols in itself when it runs. But let's say I had a function in I don't know. Actually, let's do it. I think I can do it this way. So it'd be library FMT, right? And then if I had a foreign function in here called format, and it took a format string and values, right? So this attribute would tell the compiler, hey, this lives in this image, this shared library, and this is what's going to prompt the compiler to load that shared library. Ironically, I don't even know if that compiles. If if I run it. It probably does, although the AST may not be, it works. The AST may not be 100% correct though. I can't remember if I was gonna... I was thinking along those lines, or what I was thinking. I think that's what I was thinking, yeah. So you'd have the foreign directive, you'd attribute the function itself, right? So this would look better syntactically. Which, yeah, I think that's roughly correct. Let me... my little diagnostic tool here. So that's like right at the top of the source file. Foreign. Yeah, so we have the foreign directive, we have the library attribute, and then that does an assignment to, right, perfect, right, it's an assignment, yeah. Okay, that works. Yeah, because this is the format symbol to the function expression, the prototype expression. So yeah, okay, that looks perfect. All right, yeah, so this is going to tell the compiler, hey, this is the image it's coming from, right? And behind the scenes, the compiler is going to know what platform it's running on. So it's going to, I'm actually testing streaming on YouTube Live. That's why this is not really like an official stream. It's just me testing my setup. I'm trying to get some data so I can understand like how I would do simultaneous streaming, which unfortunately like right now looks like it might be a little bit difficult, but I'm gonna try to figure it out because when I come back on the 29th, I want to try to stream on both YouTube Live and Twitch at the same time. So the tool that you just saw, that's the compiler. The compiler does that. So, so if I go into the build folder here for the compiler, so Bootstrap, that's the actual compiler itself, right? And it's kind of grown up a little bit since the last time I was showing you guys this. And so you can actually pass a command line parameter and tell it to output a graph viz file, and so it will output this, oops. When I run it through the debugger, I have it passing the command line parameter, and it generates this graph viz file from the AST. And then I take that and I just run it through the graph viz program, and it generates a PDF for me. And that's it. So it just really helps debug the AST so I can actually visually see it really cleanly. So for things like this where, you know, what does this end up looking like in the tree, it just makes life a lot easier. Okay, so here's what I think I need. Because I have a name to shared library already. So when I do a load shared library, What I need is I just need a way of getting a pointer to the shared library. So if it's not there, we return null. Otherwise, we return the address of the shared library structure that's in the map. And so then the compiler can get a pointer to the shared library. So it's good. It can load the shared library, then get a pointer to it, which I guess then technically we should just also do this. Trying to find a home for you where you fit, where you're all nice and snug. Oh yeah, I should talk about the heap stuff. That's all new. Okay, so let's do this. Okay, so if it's already, we call load shared library, if it's already in the map, we just return a pointer to it. Otherwise, we do the load on it. So this is actually going to go out, do the load library on at the operating system level. It's going to map that into our address space. We're going to get a manifest inside of the shared library of the symbols and their addresses. And well, I should say we're going to get a manifest of their symbols. We get the addresses on a as accessed level, and then we put that string and shared library combination into our map, and then we return back the address to it. And then we also have a shared library accessor, so we can pass in a path to it and get a pointer to it. So this is all in the interpreter, right? So these are things the compiler is going to use, right, to manage this stuff. And technically, we can unload shared libraries. I'm not going to worry about that too much at the moment. So this is, yeah, this is done. That's done. That I'm still thinking about. These are done. That I'm still, yeah. So let me make a note here. So low priority. Okay. So now, when we register a foreign function, what does that do? Hey, Everx, how's it going? Okay, so first, on the off chance that we pass in a signature that actually has a pointer on it, we're going to look it up. And if it's there, we're just going to return true. Because we don't want to register it twice. Otherwise, we're going to get the shared library by getting it from the signature. Oh, I already have it. Look at that. Okay. So if there is no library pointer, so what's going to happen is the compiler is going to know, it's either going to call load library or load shared library. It's going to call shared library. It's going to get a pointer to the shared library. That's either going to be the image for the compiler, or it's going to be some other shared library that's going to go load. So it's going to have that, right? Because it knows that from the syntax, right? So here we're specifically saying it's libfmt. So on a Mac OS system, it's going to be looking for libfmt.dylib is what it's going to try to load. These don't have a library attribute on them, so the compiler is going to just assume it's itself. It's its own image. But it's going to know, so it's going to see these, And when these go through the compiler, it's going to say, oh, I have a foreign attribute. Is there a specific library? Yep, there is. Okay, load that library. Did that succeed? Okay, great. Now I have a pointer to that library. Now on the interpreter, register the, this function prototype. Okay, so it's going to turn this function prototype into a function signature T, which should be a piece of cake, right? And then it's going to call register foreign function, passing in that function signature T. Now the compiler doesn't know the address of this function yet, right? The compiler doesn't know that. The interpreter does, maybe. So what's going to happen is, landscapers, it's Thursday. We're going to try to get the shared library. Now, I guess theoretically this could call load shared library for us. And we could just combine it all into one. But if it doesn't find the shared library for some reason, then that's bad. Otherwise, we have the shared library. So now I can call library symbol address, passing in off of signature the symbol for that function. Okay, so what does this do? What this does is inside of that shared library, we have a dictionary that maps, we have the symbol address map, which maps a symbol name to a pointer, a void pointer. Because again, when we load the shared library, we enumerate the symbols, we put them in the map, but we don't call DL find symbol yet, because that's kind of expensive, and some of these libraries have thousands and thousands of exported symbols, and my thought was, well, if you're only using like 3, it's a good thing to have the catalog there so we know like what functions are available, but we would call find symbol only when we need it, and then it populates that address in the map right at that point. So what this DL find symbol does is it takes the library and it takes the name and it finds the address in memory where it's been mapped to, right? So we have that. And so now we can say, well, we get the func pointer. If it's null, that's bad. And we should probably, this should probably take a result. So it can actually like put some contextual error messages in there. Because good error messages are hard to come by. Okay. Okay. So now, if we got the function pointer, then we just update the signature to have that function pointer, and Oh, and of course I can't do that because I made it const. And then it's not in the function, foreign function map yet. So foreign functions, insert, standard pair. And this is going to be func pointer and signature. Okay, so that's register foreign function. If the signature we pass in already has a function pointer on it, then we just look it up and see if it's in the map. If it is, then we return true, we're done. Because the structure that was passed in by reference already has everything on it that it needs to do this. Then, if not, okay, does the signature that the compiler constructed have a library pointer on it? Because if it doesn't, we can't do anything, right? We need to know which shared library to go look at to make sure that we're using the right library reference to get the address, right? Because again, you load shared libraries into memory. When you resolve that symbol, you're telling the library, this is the shared library I want to resolve the address for. So if library A has a symbol foo, library B has a symbol foo, you know, you can get an address for both of those independently. Even though they have the same name, they live in different libraries. And the address is going to be different for each one because the shared library gets loaded into a different address space by the loader. So we have a library, we access that shared library. And actually, if I have a library, why am I getting it? Yeah, that's stupid. I don't need to do that. Duh. Right. So if I have a library, then I can resolve the symbol. So the function signature has the name, symbol here is the name of the function. And so I can get that pointer. And that pointer is going to be unique for this execution of the compiler. And again, even if I have four shared libraries, and they all have a function called foo, they're all going to have different pointers in my address space when they get mapped in. And so I'm going to get different pointers, and our lookup table is by the pointer to the signature, because then what happens is in our FFI instruction, the very first operand is the register holding the address of the function. So actually our FFI instruction becomes a lot simpler. We don't need the flags, we don't need the number of arguments. We do still need the calling mode, but what we're going to do here is we're going to say foreign functions find address, and I'm going to do a reinterpret cast for uint 60. Oh no, I got to turn it into a voice. Right, if it's not found, then we just don't do anything. Otherwise, we'll just get the address of the function signature. Now I have all this metadata. Woohoo! And you know what? I don't need this because the vector has that information. Perfect. Okay. So now I can say switch argument dot type. And then this is DC bool arg bool, and this is call VM, and then static cast. No, I gotta do a interpret cast. Cool. Pop. Because so. Our interpreter has a stack. The dyne call system has a stack. So we're taking our parameters off our stack, which the compiler is going to have to generate backwards because we're taking from one stack and putting it on another stack, and we gotta make sure they show up in the right order. Oops. I think there's also DC arg struct. I'm not sure how we're going to do that. What is this? It's actually a DC struct. Yeah, so DynCall has an API where you can basically define a struct within it, within the interpreter. You can tell it how memory is laid out. So somehow we'll have to create a DC struct, and which means our argument type here, if it's a struct, right, we need to know what the shape of that is, because we have to be able to create it. So I think the answer there is eventually, when I have the type system more fleshed out, and there you go. For everything but structs, that's what we end up with. Lot simpler. Oops. All right, use the right, so this is not 100%, right? But right, because we have to be able to dynamically fill in the struct bits. So we're going to have auto. Okay, that's a bit closer. Right, so we're gonna, this is metadata to dyn call. It tells it what the structure of this pointer is pointing at, right? So we've got the pointer part, because that's just an address that's on the stack, that comes off the stack, no problem. What we're missing is the ability to build the structure definition. So, but that's it, that's all we're missing. Now what is it complaining about? There we go. Okay, make sure nothing broke. Hey, okay. Nice. Are nice. Yeah, so in my example code here that's being compiled, I put a library attribute in here on this foreign prototype just so it was kind of clear like how that would work, and then Surprisingly, the compiler handles that, or the parser handles that properly. I updated some of my to-do notes. And then these were bit masks, and I converted them to be not bit masks. Because I don't need them to be anymore. And then I added function argument t and function signature t. So the terp, this is part of the interpreter's interface, right? That if you want to register a foreign function with the interpreter so that the FFI instruction can call it, this is the metadata that it needs to do that. And again, we're not 100% finished here, right? You know, actually, you know, as I'm looking at that, like, why couldn't I? Why couldn't I do that? Okay. So then if I had a name and the type was struct type, and then it had a bunch of fields, then they're going to have names and they're going to have types. And then, yeah, you know, that'll work. And the compiler, you know, can build that, would be responsible for building that structure. But so then the return type would have to be a function argument too, which it, you know, kind of sort of is. Right? So it could be recursive. Yeah. So we have a function value t, which is the return type. We have an array of function value t's, which are the arguments. And okay. There you go. Okay, so now I just need a helper function that returns back a DC struct here. So the number of fields is field size, and I'm assuming the alignment is the pointer size, but I'll double check in the documentation on that. Okay. So it's DC struct field and pass the struct, and the type here is DC bool, and the alignment is size DC Hey, Overseas Media. Yeah. Let's see. hate when you have documentation, they don't make it easy for you to search. Oh, and of course the documentation's out of date. Great. I love out of date documentation. Thanks, Overseas Media. I appreciate it. There we go. What do we got? Oh, good. There we go. Bingo. Finally found some code that... So then it's DC. Where was I at? Oh, I was in the header file. That's right, because this stuff uses like a character. He can do a string thing where you pass in a bunch of characters and it tells it like what it looks like. Oh, and of course. They make it difficult, right? Oh, I see. So it would be I think that's how that would work. I don't know. There we go. Yeah, I got it right. Maybe. Oh, I see. Ugh. Okay. So you don't have to create a new struct. So here's how this is gonna. So you create a struct field, and then you create a substruct, which is still at the same level. And then we would call populate struct on that value, that instance, passing in the structure. So we open a new structure, we recurse, which that code's going to do, this code's going to recursively do that, right? So then all this does, this creates the structure, this calls populate struct, passing in that parent, right? And then you have to call this close to make it usable. And then when we're done with it later, we have to call DC free struct. So we called toDC struct on the root value, right? So if it's the return type, or if it's one of the arguments. And then if that's a struct that has nested structs, you know, then we loop through this add struct fields, loops through the fields in this instance. And then we switch on the type, so we put the right field in here. And if we get to another struct, then we add the struct field, right? So this is the field in the current instance. Then we create a substruct and we recurse for this parameter and let it populate its fields into this current struct. And then when that's done, we close that substruct off. Oh no, you're right, because this is like a reference count. So that should be okay. And then at the very end in the root call, we close it for the final time, and then we return that pointer. All right. Okay, so then, so if it's a struct, we just call value to, or whatever I call it, argument to DC struct, be const, and boom, there we go. Then what we'll do is we will keep track of the structs. So this is the same thing. So return value, func signature, return value to DC struct. There we go. And there you go. And at the end here, that. Okay, so we get the address from the first operand of the FFI instruction. This is the function we're going to call. We use that address to look up the foreign function in the foreign functions table, and if we don't find it, we got bad things. Otherwise, if we find it, what's in that table is that map is the function signature T. So we get a pointer to that, and then we check the calling mode, and I need to read through the sample code and the documentation more. Like, I'm guessing I need to support these explicitly, but I may not need to, I don't know, we'll see. The documentation says you have to call DC reset. So that this basically, so you have a block of memory, kind of like the Basecode virtual machine. So you have this block of memory that Dynecall is using to run its little internal program. This just resets everything internally, so it's clean. I have a vector that tracks the pointers to the DC structs that we create so we can free them. We loop over the arguments for the function, right? So these are the parameters to the function. And then we have to switch on the types to populate the correct argument on the Dynecall stack, right? So this is pushing these arguments onto the Dynecall stack is what's happening. And then for structures, I changed things a little bit. So this used to be function argument T. I made this function value T. We have a name, we have a type, we have a list of fields. So these can kind of sort of be pseudo structure-y things from a metadata perspective. And then I have two helper functions on here that will take this data and turn it into a Dynecall structure recursively. And so we get that Dynecall structure, we add it to our list of things to free, and then we do the DC arg struct, which this is this is the metadata. This is not the data. This is the description of what it looks like. This is the pointer. So what's on the stack, on the Basecode interpreter stack, is an address to somewhere in the heap that points at a structure that looks like this, right? And that address could be on the stack, right? There could be room on the stack that has that data in it. So this could be literally pointing at, you know, the stack pointer -8 or whatever, +8, but it could be anywhere, right? It could be on the heap, it could be on the stack. And so we're telling Dynecall at this location in memory is this thing that looks like this, right? And so then it knows when it makes its call to the native library, it has to, you know, do its magic, and that's how it does that. Then for our return type, we have to look at what that is, and the same thing happens again. And I wish I could consolidate these, but these are different function calls in Dynecall, so there's just really no way to consolidate this. So these are the things that actually make the call, right? So if it has no return type, we call void. If it has a Boolean return type, we call DC call bool. And in every case, for the most part, we're just pushing the value we get back on our stack. And our stack it's all integers, right? It's all just binary. Even if it's floating point values, they're represented as binary. It's not typed at that level. So we just take whatever comes back, push it on our stack. Then in the case of, so if we call a native function and that native function creates, its return type is a struct, okay? So kind of similar to when we're using it as an argument, we're going to get a pointer back from dyn_call. So dyn_call is going to tell us, hey, this thing that you called in this library, it created a struct for you and it put it here in memory, okay? So then what we're going to do is we build the DC struct. So again, this is the metadata that describes what it looks like to dyn_call. And then we called DC call struct, and this is the address to the function we're calling. This is the metadata describing what the structure should look like. And then we're passing in our the address of our pointer so that dyn_call can populate it with the address of where the actual data is that matches this layout. And then again, in our interpreter, everything's just addresses on the heap, right? At the end of the day. So we take that return value and we turn it into a number and we push that on the stack, right? And then other Basecode, bytecode later, it can do loads and stores and whatever from that structurally. The compiler can generate code, right, that accesses that structure within the Basecode heap. Now, the interesting thing is, though, when we're calling foreign stuff, these foreign things, they exist outside of our, they most likely, well, definitely exist outside of our heap, right? When we're passing an argument to a function, that's pointing inside of our heap. When something returns a pointer to us, that's somewhere else, right? Which is okay, but that just kind of implicitly means that, like, if we call some function from some library that returns a structure to us, a pointer to it, then that means we probably also have to make sure that we call whatever its companion freeing function is, because that memory is outside of our control. It's not in our heap. And then at the end, I free up all the structures. So, okay, that works. And that covers it. So then the compiler just has to take, you know, the structure information that we have, right? So I have this structure here. Like if I was going to pass this to some other function somewhere, you know, I would know, the compiler would know, okay, I need a 64-bit value, a floating point value, and another 64-bit floating point value, and then I need a pointer and a pointer and a pointer, right? That's what this thing looks like. And so then it's going to be able to build a, it's going to be able to build a series of function signatures that match what you know what it sees here, which is what we want. So, all right, let's go back. So I pulled in some more dyn_call header files, and okay, so then I changed the name of this. Instead of function argument t is function value. It has a name and a type and a list of fields. For a lot of arguments, fields will always be empty. But for structure-y type things, right, it will have the metadata in there that describes what it looks like. And then we can use that to create a dyn_call structure. And then our function signature, the return type, the return value now is represented by the same thing as arguments. So it's just function value t. So we have an array of those for arguments. We have one of those for a return. And that allows us to use the exact same code to generate the appropriate metadata with dyn_call. And that actually works really well. So yeah. All right. And then we added in register foreign function, which is what most of what we worked on. Then I updated load shared library to return the shared library t-pointer. And then I also added a shared library accessor. So if you pass in a path, if it's already loaded, it'll return the pointer to that. And then I added the unordered map. So this is the address of the foreign function and this is the function signature T that defines it. So this is what register function manages. And then if we add in like unregister function, right, it would take it out of this. And then if we add an unloaded library, it's going to take the shared library out of this and free up all those resources. The pointer that we get back for the function, we don't own it. That's owned by the operating system, essentially, by the loader. We're just using that pointer, we're just aliasing to it. But the shared library does have some pointers that are owned by it. And so its destructor calls the appropriate free methods to clean all that stuff up. And then register foreign function in the CPP file. You know, if our signature, so if we somehow call register foreign function and we pass in the same function signature a couple times and it's already been initialized, we just check to see that it's in the map, and if it is, we're done. If the signature doesn't have a library pointer on it, so again, the compiler is going to know what library it loads, and then it needs to assign a pointer to that, to the signature when it creates it, so that we know what library this signature came from. And primarily it's because of this, right? When we resolve the symbol address for that function from the library, we have to do it against that particular library, right? Because again, you could have 10 libraries that all have the same function called foo, but they are distinct because they live in those separate libraries, and the loader loads those into different segments of memory, different chunks of memory, and the addresses are different, right? So you can call each distinct foo, but the way we resolve that is by doing it through the library. So we look up the function pointer for that. If we don't get it, that's bad. That means that the library, we used the wrong library name, or it's not being exported, or whatever, but it's just not there. And then if we get the function pointer, we assign that to the signature, and then we insert that signature into our foreign function map. So again, the foreign function map is the pointer to the function and the signature, with the library pointer and the function pointer populated on the signature, right? And then in our FFI instruction, this is just so much nicer now, because before I was passing metadata in different arguments on the instruction, and it didn't work. So here now we definitely get the address, right, of the foreign function we're going to call, and it can be a constant or it could be in a register. I think the compiler is probably going to generate these. It's probably going to load them into registers, would my guess, but maybe it'll generate constant addresses in here. Either way, it doesn't really matter. So then we look up that foreign function. If we didn't find it, then, you know, right now the instruction just doesn't do anything. It's just a no-op, essentially. Probably, I don't know. This probably should issue a trap, right? Like, you know, trap 255 is out of memory. Maybe trap 254 could be, you know, invalid foreign function address. You know, we could reserve a couple of those, and so then if the compiler registers trap handlers for those, right, then it's going to get callbacks, right, when these things fail, and then it can decide what to do. Let's see. Right, so then if we get it, then we just need to get the address of the function signature, because we don't want to accidentally make copies and stuff of it. It's just better to just access it as a pointer. So we have to set the calling mode on dyn_call, and dyn_call has a bajillion calling modes. So what I think I'm ultimately going to end up doing is, you know, I'm going to handle like the most common cases sort of like this. The compiler is going to set these, right? It's going to know, yeah, it's a function that has var args. It's a function that has an ellipsis in it. It's standard call or whatever. But ultimately, I think what we'll probably also have is another attribute where called, you know, calling mode or calling model or whatever, and you can annotate, you know, foreign function prototypes and say, hey, use this calling mode. And then the compiler will take that metadata and populate it into this when it creates the function signature for you. Now that's a static thing in the sense that, like let's say you had a function, and I don't know why you would do this, right? I don't know why you would do this, but let's say you had a function you were going to call in some library, and in one instance you wanted to call it with just using the standard C default, and then in another instance you wanted to call it with maybe a Windows optimized calling model, okay? So what you could do in Basecode for that is trying to think of a good example here. So this is the symbol in our system that is unique or not, right? So you can define that foreign function multiple times if you change the symbol name. Now, as soon as you do that, you have to fix it, right? Like, so presumably by default this matches, without an alias, this matches the actual name of the symbol, right? But if our name internally, for whatever reason, is different, we can tell it, hey, this is the name. I'm actually kind of curious. Yeah, I didn't think it would take that. So I don't know. I have to think about that one. So I got to fix that, but why is it complaining? Expected semicolon of a found line comment. Interesting. Oh yeah, I need to shoot. I need to fix that too. I just don't have an infix parser for comments. Okay, so once I fix the alias thing, right, or fix the attribute stacking thing, I think oh crap. Yeah, no, that's why. Darn it. Actually, I think it will work. I think that was the mistake I made. Yeah. Yep. Okay. Because this is a statement, then in that case, right, this is wrapping that. So, yeah. I'll actually make another note here. So, attribute should assume multiple arguments within a statement. Right, so then I wonder if that will work. Like if I do an argument list. No. Oh, it's got any in it. Crap. Wow, I'm finding bugs. Okay, there we go. Yeah, now it's complaining about the comma. Right, okay. So yeah, I need to review the syntax on that, like how I'm handling that. I don't know if I want it to be comma separated or ultimately what I think I want is maybe something like that. And then, yeah, I don't know what you think about that. But yeah, so anyway, going back to what I was originally saying, right, this would be the symbol that we would assume to use to look it up, but this is also the symbol that binds in our local namespace, right? So for whatever reason, then we wanted to have like a calling convention, right, on this. And we want to call this, you know, C default or something. And then here, we want to use a different calling convention. We wanted to use win x86 fast or something. This would allow you to do that, right? So if you wanted this version, right, you would call format win x86 fast. Behind the scenes, right, the compiler is going to, the foreign function is going to look up its format, right? And then in this case, you get this calling convention, and in this case, you get a different one. Because the metadata on this prototype has that. This is the function in our namespace would get registered. So this prototype is distinct from this one, even though it's pointing at the same native function in both cases. Yeah. Now I'm curious, like what that actually, what it's generating there. Yeah, okay, so statement, whatever that is, I have to trace that line back. But we have a statement that has the foreign token that has an attribute. Oh yeah, so see, yeah, it's literally like at the program scope. So that's the issue. Like these need to be scoped underneath the, I mean, there's, and that's, we could do that, right? Like, I think the compiler will be totally happy with that. Yeah. And now those should be under a basic block under the foreign. But again, I'm not sure if that works, but I'm not really sure if that's what I want. Maybe not. Interesting. Oh wait, did I actually convert this? That's weird. Yeah, no, it's still... Oh no, wait. No, it's right. Okay, it's right this time. Yeah. So here's the foreign directive. And then it has a basic block. And then it has the first statement is the library attribute. The second statement is the calling convention attribute. The third statement is the assignment of the symbol format WinX86 fast to the function expression. So that works, right? But yeah, I don't know. I gotta think about how I want to do that. If I like that syntax, you know, because that's the other thing too. I guess technically, you know, you could, if they're all scoped to that foreign, right? You could do stuff like that. The trick is from AST lingo, what I want is I want these, so the PDF that you see comes from GraphViz. So the way that works is the compiler, when I call the compiler, I have a parameter that I pass, -g, and I pass the name of the file that I want it to output to. And so when the compiler runs, it looks at the options that are passed in, and if that option is set, it outputs that dot file. And the Fibonacci, I mean, I just call it Fibonacci. It just creates a GraphViz formatted file from the AST. So this is just a text document that follows the GraphViz syntax, and this defines the graph, right? And then I just run that through GraphViz, and it generates a PDF for me. Correct, yeah. I manually generate the dot file. No magic, just, yeah. Write code to do it. Yeah, so the trick is with these attributes, I really want these to be, I want them to live next to, right? So this is one statement. That's what I want. But right now the parser's not happy with that. So I need to fix that, because then this will be a statement where these bind together, and then it's clear lexically that these attributes apply to this, and then this has no attributes and that has no attributes. So yeah, that would be the thing to do. And I think I know how to do it. I think the issue is I don't have an infix parser for some of these, right? Like I don't have an infix parser for the comments, and I don't have an infix parser for the attributes. And if I put one in there, that I think will fix the problem, right? I am curious though. Yeah, no. I thought maybe that would be a clean prefix state, but it's not. All right, so I got to fix that. But otherwise, I think it's good. Okay. Well, like I said at the beginning of the stream, I really wanted to just get OBS working properly with YouTube live streaming. And, you know, I've been having some problems. I'm still not entirely clear how I'm going to be able to do like a simultaneous stream, but I'm working on that. Again, I would like to simultaneously stream at least for a while and see how it works and if there's any issues or whatever with that. Yeah, I was only going to stream for about 2 hours today just to kind of test it and say hi to anybody who dropped by. And I definitely will be back, you know, on Twitch on the 29th. So, and if I can't figure out the simulcast stuff, I will, I'll still be on Twitch, and then treat stream, yeah. yeah. So anyhow, thanks everybody who showed up, and it looked like it worked pretty good. And like I said, this will be archived and released, so anybody who missed it, you can watch it. I'll put it in the Basecode playlist. So yeah, so that'll about do it. And thanks everybody who dropped by, and I'll see everybody on the 29th back on Twitch, my home stomping grounds. All right. Oh, Restream.io. Okay. I'll take a look at it. All right, guys. Talk to you later.